Hello, welcome to Machine Learning at Home. Today I'll speak about PCA, on Principal Component Analysis, but not a typical PCA, some unusual kind of PCA. So normally when we involve any PCA in our calculation, we want to reduce the object in some understandable shape. For example, if our object has like 50 dimensions, we want to reduce it into 2 dimensions or simply project it to see how it looks. So this is exactly what PCA is for dimension reduction. And reduction of dimensions involves some understanding of the space. Normal understanding of the space is called Euclidean. So the shortest distance between 2 objects in that space is just a straight line. However, in real life, the straight line is not typically the shortest distance. Imagine you take a taxi in a town. So taxi will go on one street, then for example turn right and go another street. That's a distance, so this is not a short line. This is a kind of city block distance or Manhattan distance. So in a dist, for example, in the dist command of R, there is a Manhattan distance which uses this concept, like a city block concept. In a statistical language it's called L1 norm. So why not to use it in PCA? And this method, L1 PCA, exists. Again, it uses not a shortest line distance, but kind of city block distance. And for that particular PCA, we will need of course the new thing, the new package. So we'll make a new package, library PCA L1. So we'll load it, and if in your case it doesn't load well, you need to install it. Installation of PCA L1 involves one more thing than typical installation, because you need to install additional library for calculations, but it's easy enough. When you do it, you can do exactly what I am doing. So let us make an example of L1 PCA which uses, instead of shortest line distance, kind of Manhattan blockwise distance. So we'll need to make a new object, iris L1, and that object will be result of command L1 PCA. That command L1 PCA will take iris object without 5th column as usual, without minus, and then we need also tell how many dimensions we want. Proj dim equal to 2. For example, I need 2 dimensions, and if everything is good, that command should work without problem. Okay, it does work. And we need now to, for example, to plot, to see how it works. So plot, and then I will need iris L1 object, and I will take subset which name is scores, and then we'll colorize my plot with species. So call equal to iris species. Okay, so this looks like we have 3 species, and these species are more or less well separated. First species, Setosa, is apart. 2 other species, Versicolor and Virginica, are kind of close together. So this is a normal result. How to compare it with normal PCA? So for that, well, you need to do something more complicated. But if you have my package, things will be easy. So you need to load my package first, and then you will need, for example, to make a convex hulls first. So I will make a new object, iris h1, which will be result of function hulls, uppercase letter. And for that hulls, I will use iris L1 scores, and the same thing for species, iris species. So if everything is good, then you will see convex hulls around each species, plus some object iris h1 will contain some useful information. Okay, now you see holes, very typical, exactly as you should see in the iris data. And then I will make a summary of overlap between these holes. Iris H1, H1. And as you see, the actual overlap is close to 9%. Kind of low enough, good result. And now we need to compare it with normal PCA, L2 PCA, actually Euclidean distance, frequently called L2 norm. So this is a default. And we need to do something very similar to my previous comments, but with different counting. So we'll make, instead of L1 PCA, we'll use a command prcomp. Name of object will be iris L2. We'll use the same data, but we don't need to specify dimensions because prcomp by default will output 2 dimensions. Okay, everything went well, and then we need to plot it. And I'll actually like to see plots side by side. For that reason, I will make a command device new. Okay, and you see empty graphical window in which new plot will be plotted. So now I need to plot the same thing, very similar, but from L2. Instead of scores, my sub-object called simply X. Otherwise, everything is similar. So I see the same picture, 3 pieces. And now I need to make same holes. So I simply put arrow up on my keyboard, and I simply repeat my previous command. So holes of not scores but out of X, and output object will be H2. Okay, and finally I will make this summary of overlap of H2. Okay, actually slightly better, so about 7%. Not actually much better, similar enough, but it's interesting that you don't actually see it quite well until you calculate. Yes, actually intersection overlap between these polygons is slightly less in normal PCA than in that first L1 PCA, but otherwise method is viable, and I think there is a data sets where this L1 norm might be preferable. So you simply need to understand that PCA has some diversity inside, and there are methods which allow you to look on PCA from kind of different angle and different approach. And you actually have a tool with my package which allow you to understand how good are both methods on your data. So this is also example of how to compare 2 different dimension reduction methods. This is it for today. Thank you very much.